So let's talk about map implementations. And when we talk about map implementations, and this is with respect to our map interface, map entry, as well as the array list map that we have implemented. So that are available, right? Also the map example under your modules. Let's do a comparisons of the map implementations using, various different underlying buffers. So the first underlying buffer is array. Obviously, you can have sorted array or non-sorted array, right? So the implementation of sorting is something that you're going to have to implement. Let's also look at sorted linked list versus non-sorted or unsorted linked list, as well as the binary tree structures that we discussed from the previous chapters, and see how, generally speaking, map implementations efficiencies are with respect to these implementation details or methods. So before we look into the comparisons, let's bear in mind that when we're talking about unsorted array here, making use of a map entry, right? This is already available inside your array list map. Now, if you think about this, if an array is not sorted, and whenever you insert, right, a map entry object, so recall that your array list map is simply a array of map entries, right? So let's say if this is a map entry, there's one right there, and another instance of it here, so on and so forth. So this is array list in Java, and array list map actually just wraps this. This is array list map. Kind of wraps around this array list, right? Because this array is unsorted and there's no notion of we should be ranking, right, the map entry when they're inserted. Every time we do a put operation, recall put is insertion elements. We have to basically look at every single one of these keys that we have, right, in the array, because there is no order, right, sense of orderedness in there, to make sure that we don't have any duplicates, right? Recall, you cannot have duplicates in keys. If you do have duplications in keys, we'll be basically overriding the value associated with that key with the new one, right? So this is what happens here, right? So let's say if there is already cat is already associated with C, and now you do another put on C and cow, right? What you're doing is you're evicting, right, the old value. So that put operation then returns cat, right? So something was replaced. So that's a pretty bad use case here, right? I don't know if it depends on, I guess, your application. Sometimes you don't want any replacements, but if the replacements happens, you get notified. So in the unsorted array, this is the O of n. So O of n as in you have to go through every single one of the keys out there to make sure that there's no duplicates. So just to look at whether your key duplicates another or not is O of n, going through every single one of it. So if you look at the code here, and this put operation is right here. So illegal argument exception if k is null. Okay, so this passes that. Now, if you have k and v coming in, first of all, the first thing we need to do is construct a map entry. So this is the one that we're going to dump right into our array list. So our array list is actually map. Okay, so this is the generic array list that takes map entry as a type and to construct that array. So this, recall that your array list map also implements iterator. Actually, no, I think what happens is your map interface, if you look at map interface, it extends iterable. So iterable is the Java interface that requires you to implement what's called the iterator, right? There's an iterator. So it gets you an iterator right here, which is a map.iterator. The map.iterator is part of the array list that allows you to iterate through its array elements. So every single one of the array elements coming out as a map entry. And the reason why we're doing this is because recall that when we insert a map entry object, we want to make sure that there is no duplication. So this checks to see that there is no key being equal to the one that you're passing in, right? If so, there's duplication, then you have to remove it, and then you return the value of what it was before. So this is O of n right there, right? Going through this entire while loop is pretty expensive. If there's a million elements, you have to go through this 1 million times in the worst case scenarios. Otherwise, if no matching, return all. So that's pretty much it. The put operations. So let's go back to here. That's what happens on a sorted array. So if we go back to the sorted array fashion, I'll recall when you have something that is sorted, your efficiency gain, right, on this data structure would be in terms of the ability to find, right, the operation. So find operation is get as well as contain. So contain checks, right, for the existence of this key. Get gets the value associated with the key in the sorted array. So this is all log n, right? So this is efficient, but everything else is the same, right? But the only cost, right, is that at insertion, you're gonna have to make sure that, basically insertion means put. You have to make sure the elements are inserted in the correct spot, right? So the cost for doing the business is insertion, but the benefit in gain is your retrieval, right? So there's a trade-off between the two. That's what happens when your underlying data structure for your map is an array. Let's look at what happens when your underlying buffer is a linked list. Now, same thing with the previous example. Let's talk about unsorted and then also sorted linked list, right? So if your linked list is not sorted, it's simply just acting like an array, because you basically have no choice. In order to iterate through the linked list, you have to go through it basically one at a time, right? You don't keep track of your front and then back, and there's no such thing. So you start out from the very first, which is the head of your linked list, and you iterate through it n number of times, right? So sometimes, this data structure as compared to array has an advantage, because with a linked list, you can dynamically, resize it, right? So resize basically says, if I'm going to get rid of, like this one, right? Then in memory, I'll have 2, right? As opposed to array. Array is fixed. So basically, even though we're using array list and that one is dynamically, resizable, but still, memory, allocations happens at the front. So you have a fixed size. It's not with the array list, right? This is array list. You can't just delete this node and say, hey, I don't need this anymore at runtime. So this is the reason why the advantage happens when you have a linked list, right? But in terms of, lookup, and in terms of, doing a contain, these things, they're similar in actually exactly the same in terms of the efficiencies O of n, right? There is no log n, notion of log n, because we're not doing binary, right, here. Sorted linked list. Now, this is interesting. I would argue there's no really, unless you have a business requirement, a need to sort these linked list elements. To me, it's really, really, it's a bad practice. First of all, you don't really keep your list sorted in a linked fashion, right? Because there is no way for you to do binary search, right? The reason why you want to sort it is so that you can, gain some efficiency. But since with the linked list, you don't just jump into a specific location and do a determinations there on the path it takes. You have to go through it one at a time. So it's O of n. So even if you do decide to sort the list, which is expensive, because to slot your value at a certain location, you have to iterate from the beginning of the node, right, all the way through. So it's O of n right there. And your lookup, right, later on insertion and lookup remain O of n. So having it sorted versus not sorted doesn't really matter. In this case, your worst case is always O of n. So making sorting a linked list unnecessary, right? So that's what this is. So let's look at the very next one. Now, if your underlying buffer is neither an array or a linked list, then what you can do is you can build a tree. And this tree is what we call a binary search tree. You don't want to do a binary tree. You want to do a binary search tree, right? Binary search tree has a property where the value of a node is always greater than the values of any of the nodes to the left of its subtree. to left subtree. And the value of your node is always, or root node, right, is always less than the value of any of the nodes inside the right subtree. So that's binary search properties. As you can imagine, the search, right, if you use that as a basis, you know exactly where to go. Either you go this way or go that way. And by the time you land around here, you know exactly whether you should go this way or go that way. So every time you do that decision, and especially when you're implementing this as a balance, right? Having this implementation in a balanced binary search fashion, then that's automatically a guarantee of the efficiency, because you're effectively, because the tree is balanced, right? You can't say there's like 5 nodes here and only 1 node's on the right side. So that's not balanced. But in a balanced fashion, right? You're guaranteed to split, right, your domain in half, right? Any junction, right? Any inner node junctions, you're guaranteed splitting, the decisions exactly at the half point. So this is the reason why you have log n, which is super fast, right, compared to O of n, right? I don't want you to think in terms of a couple of nodes here. We're talking about n being super large, right? A couple of millions, several billions, right, in general. And this is the benefit. So lots of times you see binary search implementations in the map fashions, and the opportunity to do so requires that you have these implement as a balance, right? As balanced as possible. Sometimes you can't make it perfect, but as balanced as possible, such that the information can also be compared, right? There is a way you can enact some sort of comparable or comparator against the key, right? Again, we're doing comparisons on keys, right? So with respect to map, these comparison happens on keys, not the values, but the keys, right? Because keys are supposed to be in a set, no duplications. Okay, let's clear the drawing. Let's move on to the next one. So the very last part about this implementation is the array list map. We went through this earlier before. In addition to put, there's also get as well. So let's just briefly kind of look at this. So what is get? Well, get means that you have to go through every single element, right, inside the array. And that calls for iterations of all of the map entries here. Okay, so your map is your underlying array list, and this array list is an array. So you can write a iterator here that goes through every single object inside of this map and checking to see if the key equals, right? So this is a deep comparisons here to see if the key matches that. And then if so, it returns a value. Otherwise, returns null. So this is a get, and that was put. And this is, let's look at the remove. So because of the use of array, your remove is also O of n, right? So remove means that you have to check to see if you have found the key. So this goes through the entire iterator. Again, this map.iterator is your native Java array list, right, iterator. And then you can invoke is has next and also next, and checking to see the key to see if that's equal to k, which is the one that you just passed in here, to see if this equals that. If so, then removes it. If not, then once you remove it, you got to return the old value, right? So if you inserting a cow, right, you got, and the original value was a cat, you got to remove that value. You got to return that value. Otherwise, it returns null. So that's that. And contains is the same thing, because there is no binary search. Return the contained here calls for iterating all of the map entry objects, checking to see if this is equal or not, and then it returns a true or false according to the result. Is empty, check to see array list. This is the native Java array list dot size. If this is null, yes, it is empty. False, no, because if false, so this array list is dynamic sizable, and because it uses array list, it's never full, subject to memory constraint. Map size is the same as the size of the array list map wrapper is the same as the map.size, which is your array list in Java. And notice that like I said before, your array list implements map interface. If you go to map interface, it says it extends the iterable, but because map interface has the iterable, and because array list map implements map interface, which means it also implements iterable, you have to override this method called iterator. So go to your Java implementations SDK in there, you'll see it. Like we said before, the iterator returns an iterator object, and this iterator object, as it turns out, sits inside your array list. So array list actually implements it iterable too. So you have basically an iterator for free that you can get out of this map. So this map all the way up top is an instance of array map. Depends on how you construct it. You can use the start within initial capacity, or you can use the default. Okay, and each object inside the array list buffer is a map entry object of key value pairs. So this is your array list map on the in summary. So this wraps our map implementation discussions.